Next, we will focus on a few reactions of dienes. In this video, we'll take a look at some addition reactions, and then later we'll take a look at the Diels-Alder reaction. Another reaction we looked at last semester was the reaction of alkenes with HX, and this one is an example of electrophilic addition. So let's say we have propene and we treat it with HX. So remember, an alkene is electron rich, and then with HX our hydrogen is going to have a partial plus, our halogen is going to have a partial minus, so the alkene can share its electrons with the hydrogen atom, pushing away X as the leaving group. So that will give us two options. We can have the extra hydrogen connected here, which gives us this carbocation, or we could have the new hydrogen here giving us this carbocation. Think about the double bond as a door, and then there's got to be a hinge. So if this is the hinge, then the hydrogen becomes connected here, and then this is the open part of the door, which is the carbocation. If this is the hinge and the door opens this way, then that's where the hydrogen is connected, but that leaves this position as the carbocation. Well, we know that a secondary carbocation is much more stable than a primary, so this one is going to be really hard to form, and so the top carbocation will be the major intermediate that's formed. So now when X minus adds, it will share its electrons with this carbon, leading to this product. So remember, this proceeds through Markovnikov addition. The alkene carbon that had more hydrogens originally gets the new hydrogen, and the alkene carbon that had fewer hydrogens originally gets the other group. Okay, but it's because of the more stable carbocation. Now, what happens when we take this reaction and we apply it to conjugated dienes? So here we have 1,3-butadiene, and it turns out when we carry out this reaction, we treat it with HBr, we get a mixture of products. And it's not really obvious because so here it looks like out of these two alkenes, this is the one that reacted, and we got HBr adding this way. But here, our double bond is in a new location. All right, so it's not really obvious what's going on here, so we need to take a closer look. Well, because this diene is symmetric, it doesn't really matter whether the first alkene or the second alkene is the one that reacts. But let's just imagine that this pair of electrons reaches out to grab the proton, and bromine leaves with the electrons it used to share with the hydrogen. Now, which way is the hinge going to open? If it opens from here, and the hydrogen is connected there, then we get a carbocation at this position, which is not only secondary, it is also allylic. So that's the way it's going to happen. So we get a CH2, double bond, CH, single bond, CH, single bond, CH2, now connected to a hydrogen, and this carbon is a carbocation. But we can draw another resonance structure where we imagine these electrons move here, which gives us the CH2 carbocation, single bond CH, double bond CH, and then the CH3. So that's what we have here. This resonance structure is this one, and then this resonance structure is this one. Okay, so even though we're only forming one carbocation because it's a symmetric diene, we get the most stable carbocation, the allylic carbocation. Still, that positive character is shared at two different positions. And if we look at this electrostatic potential map, we can see that there's a lot of blue character around here, that's positive character, and around here. So now when bromine adds, bromine can add either at this position, which leads to this product, or at this position, which leads to this product. This product corresponds to this product, and this is called 1,2 addition. Because if we call this carbon 1 where the hydrogen adds, then carbon 2 is where the bromine adds. And then this one corresponds to this product, and this is called the 1,4 addition product, because if we call this hydrogen 1 where the hydrogen added, if we call this carbon 1 where the hydrogen added, this is carbon 4 where the bromine added. So it's 1,4 addition. For this simple diene, the mixture of products reflects the contributions of the different residence contributors. So let me erase this just so we can see a little bit better. All right, now here we have, if this resonance structure existed, it would have a primary carbocation. If this resonance structure existed, it would have a secondary carbocation. This one would be the major resonance contributor. Therefore, the resonance hybrid would have a small amount of positive character here and a big amount of positive character here. Therefore, the bromine would rather attack this position than this position, which gives us the 1,2 addition in this case as the major product. Now, another thing to keep in mind when we talk about 1,2 versus 1,4 addition, we are talking about the position of the groups relative to the diene, not relative to the IUPAC name of a particular compound. So for this compound, we have the alkene at carbon 2 and carbon 4, but if we add HBr and we isolate some of this product, this would be the 1,2 addition product, because this is the first carbon of the diene, this is the second carbon of the diene 3 and 4, and so for this product the hydrogen added to carbon 1 and the bromine added to carbon 2 of the diene. So just keep that in mind, that you can have 1,2 addition even though that puts the hydrogen at carbon 2 and the bromine at carbon 3 when we're thinking about the IUPAC name. Other types of electrophilic addition reactions to dienes can also give a mixture of 1,2 and 1,4 products. You have to be on the lookout for that. A really interesting thing about this particular reaction is that it also gives us an opportunity to explore different ways of controlling the major product in a particular reaction. So again, remember, this is the 1,2 addition product and this is the 1,4 addition product. And down here we have an energy diagram corresponding to this reaction. So here we have 1,3-butadiene, and when this reacts with H+, it forms this carbocation. Now from here, it is faster for the bromine to add to this position because that position bears more of the positive charge. So for example, we could rewrite this as this one has a big partial plus and this one has a little partial plus. The way that translates into the reaction is that the transition state leading to 1,2 addition, here's that transition state, and so here is the activation energy leading to that. Other carbon has a smaller partial plus. Well, for the bromine to add there, it has to overcome a higher activation energy. So this is the transition state leading to 1,4 addition. And so I'm just going to move this over here. And now we think about this has to go up and then down. So this is the activation energy leading to the 1,4 product. If this reaction is carried out at low temperature, then once the molecules have enough energy to overcome the first activation energy to reach the carbocation, then this reaction, this molecule will then follow the easiest pathway, right? So it will go this way rather than trying to climb a higher mountain to give this. All right, so at low temperature, fewer molecules will have enough energy to overcome the higher activation energy, and so whichever product is formed fastest is going to be your major product. So that is called kinetic control of a reaction. Kinetic control, you carry it out under conditions that give you whichever product is formed fastest. Now, still looking at this particular reaction, notice when we have our 1,2 product compared to our 1,4 product, the 1,4 product is at lower energy. Here we have a disubstituted alkene, which is slightly more stable than a monosubstituted alkene, so this product is more stable. If we're carrying out the reaction at low temperature, it doesn't matter who's more stable, it only matters which one is formed faster. If we want to get mostly the 1,4 product, then we can carry out the reaction at higher temperature. At higher temperature, well, it's still going to be, so the reaction happens, we get the intermediate, and then this is formed. But at high temperature, then this has enough energy to go back and then to go forward this way. So at higher temperature, the reaction can reach equilibrium, and then it equilibrates to the more stable product. And so that is called thermodynamic control. Thermodynamic control. So by controlling the reaction conditions, you can maximize your yield of 1,2 product by carrying out the reaction at low temperature, or you can maximize your yield of the 1,4 product by carrying out the reaction at higher temperature using thermodynamic control. Now, the drawback about learning about kinetic versus thermodynamic control is that for this particular reaction, the 1,2 product is the kinetic product and the 1,4 product is the thermodynamic product. So it is always true that whichever product is formed faster is called the kinetic product. Whichever product is more stable is called the thermodynamic product. But the problem is that in other related reactions even, the same product might be the one that is formed faster and the one that is more stable. So for example, if we had an energy diagram, let's say this is our intermediate, maybe this one is formed faster and it leads to the more stable product, whereas the other option has a higher activation energy leading to a less stable product. So if this energy diagram represented a particular reaction that you're investigating, then the black product would be the kinetic product because this would be formed in preference at low temperature because it's formed fastest. But the black product would also be the thermodynamic product because this is the most stable, and so when the system is allowed to equilibrate, it will equilibrate to the black product, not the green product. But here again, we're seeing another, well, both the advantage of an allylic carbocation, right? So reaction of a diene can lead to an allylic carbocation, which has the advantage of being stabilized by electron delocalization, but that leads to another disadvantage where we could have a mixture of regiochemistry of our reaction products. In some cases, it is possible to control which regiochemistry you get, right? You might be able to maximize your 1,2 product, or you might be able to maximize your 1,4 product by taking advantage of either kinetic control or thermodynamic control, right? For all of these electrophilic addition reactions, 1,2 is always the fastest, and so 1,2 is always kinetic control. But the 1,4 product, in this case, it is more stable, and therefore it would be the thermodynamic product. But for other starting materials, the 1,4 product might not be more stable. So when it comes to reactions of dienes, I want you to recognize that many of the reactions of alkenes that we saw last semester can also be applied to dienes or trienes, etc. But there could be differences that come about in terms of the exact conditions that are required, or there could be issues of regiochemistry as we see in this particular example.